So this is called a logistical graph curve, where your populations are dependent on your resources and a finite amount of resources for their survival. You only have so much food, you only have so much water. This is going to limit your exponential growth to a certain point. So you're going to have this exponential growth for a while, and eventually they're going to be competing with each other for those resources. So that's why we get this S shape right here. So here's another depiction of it. This is a little bit more typical. A lot of times you don't have this massive lag phase. A lot of times this lag phase is actually pretty short, depending on the population that is introduced to this new area. So you've got this very slow lag phase. Your carrying capacity is here by K. You've got this exponential growth up. They're now starting to fight for resources. They're starting to compete. So they're not having as many births surviving, or you're not reproducing as much, and you've got this leveling off. This graph is a little bit off just because, like I said earlier, this carrying capacity should actually be just a touch above this for a real world implication, but for our purposes, this is just fine. We have another set. It's called a J-shaped growth curve. This is for organisms whose populations are going to start very small. They're going to lag for a while, and then it's going to increase really, really quickly to the point where they are going to surpass the carrying capacity of their ecosystem. Yes, this can happen. You can absolutely surpass the carrying capacity, but once you surpass it, what happens is that there's a massive crash. Remember, a habitat can only sustain so many individuals. If there are more individuals there than the habitat can support, you're going to have a massive crash in your numbers. The population is going to die off very quickly. You're going to have a lot of different age groups dying very quickly, not just the old and the sick. So this is what we're looking at. So pretend there's a lag phase right here. Pretend it goes a little bit flat and then it comes up. Here you've got your exponential growth. Here is your K. Here's your carrying capacity. This has increased. This has increased to the point where it's so crazy. Oh no, we're out of resources. There's this drop. Goes up, drop, up, and drop. This is usually shown with animals who have a very fast reproductive stage, and who also reproduce a lot at once as well. So very high litters. So there's a lot of factors that are going to act to slow the growth of a population. These are your limiting factors. If you took chemistry, you think back, I know you all hate it. If you think back to stoichiometry, there was a limiting reactant. This is kind of the same thing. There's limiting factors. So factors that are influenced by the population size itself, these are called density-dependent factors. Predation, huge, huge, huge. Diseases, lack of food, lack of water, lack of space and shelter for them. Accumulation of waste, a lot of people don't really think about this, but especially in aquatic environments, this can be really, really important. If you have a lot of waste, you've got a big uptick in your nitrogen levels, which means that the fish aren't able to survive very easily. The larger the population, the bigger the problem. If you just think about, you've got 2 boxes of cereal and you've got 2 people. Those can be shared pretty easily. It can last a couple of days too if you really need it to. Now, if you still have 2 boxes of cereal and you've got 100 people and like 1 spoon, that's not going anywhere. Everyone's going to fight. People are not going to go hungry because there's only so much to go around. All right, so look at number 2. So factors influencing the population size regardless of how big to small the population is. These are density independent factors. So weather, natural disasters, human disturbance, pollution, and all that stuff, hunting. So these up here, these number 1, depend on the number of individuals in a population. So if you have more people, if you have more individuals, you're going to run out of food, you're going to run out of water, you're going to run out of space. But these factors down here, hunting, habitat destruction, pollution, natural disasters, those have absolutely nothing to do with how many individuals you have in this population. So another thing that you've got is a short lifespan as well that can cause this. So you've got this massive jump. So think about rabbits. You've also got a high infant mortality rate. They're going to have a lot of individuals or have a lot of offspring to try and offset this. So you've also have more individuals migrating out of an area, which is emigration, than into an area, which is immigration.